Hello everyone, this is the video series on OPAMP by Professor T.S. Square. In the first video, we have learned about the basics of OPAMP, non-inverting and inverting open loop OPAMP. In the second video, we have learned about the closed loop configuration of OPAMP, summing amplifier, OPAMP circuits with resistors and capacitors. This is the final video of the series, and in this video, we'll learn about multiple OPAMP circuits, spatial OPAMP circuits, and positive feedback OPAMP. If you are watching this series video for the first time here, then I recommend you to watch the video in series for having a better understanding. Let's start. Now we will discuss circuit consisting of multiple OPAMPs. Whenever a circuit consists of multiple OPAMPs, the best strategy is you try to look at the OPAMPs individually. Let's say this OPAMP, I'll call it OPAMP 1. For this OPAMP 1, input is given at the non-inverting terminal. The other terminal is grounded and there is a negative feedback here. So this input Vi will be amplified and the output obtained will be given by the closed loop non-inverting formula. Now, the output obtained here is fed to the next OPAMP at the non-inverting terminal. So, and if we focus on this OPAMP, the input is given here, the other terminal is grounded, and there is a negative feedback. So, this is acting like a closed loop non-inverting OPAMP. So, by using the formula of closed loop non-inverting OPAMP, and using the expression of the signal obtained here, we can find out the final formula. So now let us try to derive the expression. So I'll call this as OPAMP 1 and this one as OPAMP 2. So here the output obtained, let me call it V01, and the same V01 is given as an input to OPAMP 2. So if we focus on OPAMP 1, V01 will be equal to 1 plus R2 by R1 into Vi. Now this V01 is fed as an input to OPAMP 2. So in OPAMP 2, the circuit configuration is closed loop non-inverting. So the output will be given by 1 plus R4 by R3 into V01, because V01 is going as an input to OPAMP 2. Now we can substitute the expression of V01 here. So it will be 1 plus R2 divided by R1 into V input. So this is the expression of the output. Now suppose if from this terminal, if it is fed to this terminal and this terminal is grounded, so in that case V01 is applied at this terminal, so the output will be determined by the closed loop inverting OPAMP formula. So like this you can solve circuit with multiple OPAMPs. We are given a circuit here with multiple OPAMPs, and it is given that this circuit, it is a band pass filter, and in order to get a lower cutoff frequency of 150 Hz and upper cutoff frequency of 10 kHz, we have to find the value of C1 and C2. Now first let us try to understand what is a band pass filter. Now in the band pass filter, suppose if we draw a gain versus frequency, then the filter will allow only frequency signal which lies within this range. This is an idealized filter plot. Now this FL is known as the lower cutoff frequency and FH is known as the upper cutoff frequency. Generally, the band pass filter will consist of two filters. The first one will be high pass filter and the second one will be a low pass filter. Now when we combine these two filters, we can get a band pass filter. Now let us come back to this circuit here. Suppose I'll call this as OPAMP 1, and in this OPAMP we can see the input is fed to an RC network, and this is a closed loop non-inverting configuration. But this RC network here, this is a high pass filter. And if we go to the second OPAMP, the output from OPAMP 1 is fed as an input, but it is fed through a RC network, and this RC network is a low pass filter. And we have already learned from our second video that the frequency will only depend on the RNC at this network. So here the first, I'll call this as OPAMP 1. The first OPAMP is behaving like a high pass filter and the second OPAMP is behaving like a low pass filter. Now for this high pass filter, the frequency which is going to be the lower cutoff frequency, it will be equal to 1 by 2 pi RC1, and for this second OPAMP, the higher cutoff frequency will be equal to 1 pi RC2. Now in the question already FL is given, that is 150 Hertz, and higher cutoff frequency is also, upper cutoff frequency is given as 10 kilohertz. Now the FL will be given by this formula 1 by 2 pi RC1. So from here we can calculate C1, and for upper cutoff frequency it will be equal to 1 pi RC2. So using this relation we can calculate C2. So that's how you can calculate C1 and C2. Okay, now we will discuss some spatial op-amp circuits. We will start from here. Here the input is given at the non-inverting terminal and the output is directly fed to the inverting terminal without any resistors. Now let us try to calculate. This circuit is just like a closed loop non-inverting. So we already know the formula, that is V0 is equal to 1 plus RF by R1 into V input. Now R1 is not present here. So it is just like the resistance R1 is tending to infinity. So if we take the limit, then we can get V0 is equal to V in. That is, the output is equal to the input. Such type of circuit is known as the voltage follower circuit. Now let us move on to the next circuit. So input is applied here and through the capacitor a feedback is given and the non-inverting terminal is grounded. Now we can use the golden rule which we have learned in the first video. So this one will be 0 volt and this one will be 0 volt. And let the current flowing through R be I. So the voltage across the capacitor, V cap, we can write Q by C, and this is equal to 0 minus V0. So V0 is equal to minus Q by C. Now the expression of the current is I is equal to V input minus 0 by R, that is Vi by R. Now in the expression of the output V0, the Q can be written as integration I dt, and if I substitute the value of I, then I will get minus 1 by RC integration V in by dt. Now, if we see this formula, we can say that V naught, that is the output, is directly proportional to the integration of the input. So this is basically a integrator circuit. The output will be given by the integration of the input. Now let us move on to the next circuit. We can apply the golden rule. So this one will be 0 volt, this one will be 0 volt. And let's say the current flowing through R is I. So the voltage across the capacitor. So voltage across the capacitor, V cap will be equal to Vi minus 0. So this is Vi, and V cap we can also write as Q by C. This is equal to V input. Now what about the current flowing through R? Current flowing through R we can write as I is equal to 0 minus V naught by R. So V naught is equal to minus IR. Now I can be written in terms of Q. The expression I we can write as dQ by dt. So if I substitute this, if I substitute Q from this expression, then I can get minus of RC and the derivative of input with respect to time. Now, if you see this formula, we can conclude that V naught is directly proportional to the derivative of the input. So this is a differentiator circuit. Now these two circuits are very different from the circuits we have analyzed till now, because we have a diode. Here it is in the feedback path, and here it is at the input terminal. Now for such type of circuits, first let us try to recall the concept of diode. For a diode, the current flowing through the diode is given by the saturation current into exponential Q into the voltage across the diode divided by the Boltzmann constant into temperature minus 1. So this one we can approximate as Is e to the power QVD by KT. So this formula will be using to find the relation between the output and the input. Now let us come back to the circuit on the left hand side. So we can use the golden rule, which we have learned in the first video. So this one will be 0 volt, this one will be 0 volt. And let's say the current flowing to R is I. So I will be given by Vi minus 0 by R. So I is equal to Vi by R. Now the same current will be flowing through the diode. So this I can approximate by the saturation current into exponential of Q into, now here the voltage across the diode is, the voltage across the diode here is this, is the difference between this voltage and this voltage. Now since this is 0, so we can write the voltage across the diode to be V naught. So V naught divided by the Boltzmann constant into T. Now if we use these two expressions, we can write VI by R is equal to Is into exponential of Q V naught by KT. Now, if you see this formula, then we can say that output is proportional to the log of V input. So basically this circuit is a log amplifier, or you can say logarithmic amplifier. Now let us come back to the circuit on the right hand side. We'll be using the same concept here. So the voltage here is 0 volt, here also it will be 0 volt, and let's say the current flowing through R is I. So I can be expressed as 0 minus V naught by R. So I is minus V naught by R. Then what about the same current will be flowing through the diode? So I can be written as Is, that is the saturation current, into exponential of. Here the voltage across the diode will be the difference between this voltage and this voltage. Since this is 0 volt, so I can say the voltage across the diode is the input voltage. So this will be Q into V input divided by KT. So using these two expression, we can write minus V naught by R is equal to Is exponential of Q V input by KT. So if you see this formula, then you can write V naught is proportional to exponential V input, that is anti-log. This is an anti-log amplifier circuit. In this question, they have given that y and x are related by this relation, that is y is equal to log of x, and we have to identify the circuit that can give an output voltage that varies linearly with x. So we have already learned these circuits few moments ago. So the option A, this is an integrator circuit, so V naught will be directly proportional to integration y of dt. What about the second circuit, option B? This is a log amplifier, so V naught will be equal to log of y. Here y is the input. What about the third circuit? This is an anti-log, so V naught will be equal to, or V naught will be directly proportional to e to the power y. What about the fourth circuit? The fourth circuit is a differentiator circuit, so V naught will be, this one I should have written proportionality. V naught will be proportional to dy by dt. Now, if you see the four mathematical expression in option C, since y is equal to log of x, so this will be e to the power log of x. So this one will get x. So V naught is directly proportional to x. So the circuit given in C can produce an output which varies linearly with x. So in this circuit, the expression of the current flowing through the diode is given by this relation, and V is the voltage across the diode, and the input, for the given input we are told to find the output voltage. Now we can apply the golden rule here. So this one will be 0 volt and this one will be 0 volt. If suppose IR is the current flowing through the resistor R, and let's say ID is the current flowing to the diode. So IR will be equal to ID, and IR is given by V input minus 0 by R. This will be equal to the current flowing through the diode. They have already given the mathematical relation, so we can use this. So it will be IS into e to the power Q. Now the voltage across the diode, the voltage across this diode will be the difference between the voltage at this point and this point. Since this is 0 volt, we can take the voltage across the diode to be V output. So instead of V, we can write V output divided by KT minus 1. Now, using this relation, you can pause the video and express the output in terms of input. So you'll get the final answer. The output will be equal to KT by Q into log of V input by R into IS plus 1. So this is the expression of the output. So in this question, a circuit is given and it is said that the voltage across the diode, when it is in forward bias, it is 0.7 volt, and when it is reverse bias, no current flows through the diode. The input is a sinusoidal signal of frequency 50 Hz and RMS value is 1 volt. Now, if the diode is reverse bias here, then zero current will be flowing. Now, let us assume, let us take an assumption that, let's say the diode is forward bias. So, the voltage at this point will be 0.7 volt, and the voltage at this point will be 0 volt by using the golden rule, which we have learned in the first video. So, if the current flowing here is I1 and if the current flowing here is I2, so I1 will be equal to V input minus 0.7 divided by 20 kilo ohm. Now, the input. Now, since the RMS value is given, that is 1 volt, we can calculate the peak voltage, that is root 2 times of VRMS. So it will be 1.41 volt. So now let us take the maximum value. So I1 will be equal to 1.41 minus 0.7 by 20 kilo ohm. So if you solve this, then you'll get I1 is equal to 0.035 ampere. What about I2? So I2 will be given by 0.7 minus 0 divided by 10 kilo ohm. So if you solve this, you'll get an answer of 0.7 ampere. Now, if you see carefully, here I1 is equal to 0.035 and I2 is equal to 0.07. That means the current is increasing when it is flowing towards 10 kilo ohm. So this is not possible, because if the diode is in forward bias case, then some current has to flow through this path. So the assumption which you have taken that the diode is forward bias is not correct. So the diode is not turned on at all. That is, the diode is not forward bias at all. So the answer will be, the closest answer will be 0 ampere. That is option C. So in this circuit, an input voltage is given and the magnitude of the input is less than the V saturation, and the ideal and the diode which is connected here, it is an ideal diode. Now the input waveform is given here, and let us denote the peak point here, A, B, C and D. So initially the input is increasing, so the output will also increase correspondingly, and the capacitor will start charging. Once it reaches the peak point, then the input is decreasing, so the output will also decrease, but the voltage across this capacitor will still be maintained at the peak value of A, and this will be maintained till the output value crosses the peak value. So basically this circuit is a peak detector circuit. Now we can draw the output. I'm drawing the output in the same graph with orange color so that it will be easy. So initially the output will increase and reach the peak value. Now after this it will maintain a constant value here, but after this point here, the output is increasing beyond this peak value. So this will again increase here till it reaches the peak point B. But after B, we can see all the input signal are lesser than the peak value. So we'll get a constant output. So the orange curve is the output of this circuit. Now, compared to all the closed loop feedback op-amp which we have discussed till now, this circuit is different. Why different? Because the feedback is applied to the non-inverting terminal. This is a positive feedback op-amp. In positive feedback op-amp, the output will always be driven to either plus V saturation or it will be driven to minus V saturation. Now, if the saturation voltage is not given, then we can consider the power supply voltage. Now, when it will be driven to plus V saturation or when it will be driven to minus V saturation, that will depend on two threshold voltage. One is the upper threshold voltage, another one is the lower threshold voltage. Now the upper threshold voltage is given by R1 divided by R1 plus RF into V saturation. Next, the lower threshold voltage is given by R1 divided by R1 plus RF into minus V saturation. Now once we identify these two threshold voltage, now to understand the role of these two voltages, let us refer to this plot. Here we have a time varying input signal, and this is the V upper threshold and this is the V lower threshold. Now if you see this plot, when the input voltage is increasing, it will remain in the plus V saturation until it crosses the upper threshold. And when the signal is decreasing, it will remain in the minus saturation until and unless it goes beyond the lower threshold. So from here to here, it will remain in the plus V saturation. Here the input is increasing, but it is not crossing the upper threshold, and from here it is decreasing and it will still remain in the minus saturation. After this point, the input is lesser than the lower threshold. So from here again, the output will go to plus saturation and it will remain in plus saturation until this point. So if we try to plot the output, so maybe I can draw a vertical line here, and here another vertical line, and one more here. So in the output, let's say this is plus V saturation and this is minus V saturation. So till here it will remain in plus V saturation. Maybe I can use a different color here. Okay, so it will remain in plus V saturation. Then after this point, it will go to minus saturation. Then at this point, again, it will come to plus saturation. Then after this point, it will again come to minus V saturation. So this is the output. Now let us try to solve this. This here, the feedback is given to the non-inverting, so it's a positive feedback, and they have not given the V saturation, so we can assume the V saturation to be equal to either plus 10 or minus 10. So now we know that the output, since it is a positive feedback, the output will be driven to saturation. Now we have to calculate the upper threshold. So it will be 1K divided by 1K plus 4K into 10 volts. So this one will give plus 2 volt, and the lower threshold will be equal to 1K divided by 1K plus 4K into minus 10. So it will be minus 2 volt. So now the input signal is given here in yellow color, and we have to draw the output. So it will be either in plus 10 or minus 10. Now we have to identify when it will be plus 10 and when it will be minus 10. So now if you see this plot, the input is increasing. So when the input signal is increasing, until and unless it crosses the upper threshold, that is plus 2 volt. So from here till here, it will be in plus saturation. Then when it comes down, when it goes lower than minus 2, there it will go to plus saturation again. So maybe I can use, okay, so one crossing point is here. I'll call it A. The second crossing point here is B. Then again we have another crossing point C here. Then one crossing point D. So this point A, B, C, D, these are the point where the transition will happen. So here I'll just draw a vertical line here. Another at the point B. Another at point C. And one at point D. Okay, now we can plot the final answer. So from 0 to point A, it will go to plus saturation. Then after this point B, point A, it will go to minus saturation. Then after this point B, it will again go to plus saturation. Then after point C, it will go to minus saturation. After D, it will again go to plus saturation. So this is the answer. This question was asked in GATE 2022. We are given an OPAMP circuit, and input signal, time varying signal is applied, and the saturation voltage is given plus minus 10 volt. Now if we look at the circuit, the feedback is applied to the non-inverting terminal, so it is a positive feedback signal. So even if the signal is a harmonic signal, the output will be switching to plus saturation or minus saturation depending on the upper threshold and lower threshold voltage. So this is not the right answer. It cannot be 0 volt also, neither it can be a constant of 10 volts. So this is the correct answer.